Hi, and welcome to week 4 of chemistry on Apex with unit 9 and transferring energy. We're into the 9.2.3, the study. So let's click, and we're calculating enthalpy today. So we've learned that graphite and diamond are both solid and they're both carbon atoms. But you know you can make a diamond out of graphite. Now, we talked about this in Earth systems before. Diamonds, making diamonds, you need something, you need heat, you need pressure. To make that. So let's think. Do you think the reaction shown above is endothermic or exothermic? What did I just say? To make a diamond, you needed heat. So if you're taking in heat, and no, it's entering in heat, endothermic. So let's just kind of review from before. Okay? So, let's review a little bit more about this. Okay. So we're talking about adding energy, turning it into diamond. We do some calculations. These involve enthalpy values. So again, we're going to be doing some math in this. The enthalpy of reaction measures the energy stored in the bonds of the products and the bonds of the reactants. Okay, so to be specific, that this whole enthalpy of reaction is the difference of the enthalpy of formation of the products and the enthalpy of reactants. So let's look at this. So look, you're subtracting. Okay, so reaction takes place in which the products, enthalpy of products, is greater than the enthalpy of reactants. Meaning, in the end, and if I go back to looking at endothermic versus exothermic of the last quiz and the last video I just did, I remember that endothermic is positive. Meaning, if I subtracted these two things, I'm going to get a positive number. Okay, so the products is greater. So like, say if I had 5 being the change of energy for products, and I subtract from my reactants having 2, it's a positive 3, meaning, the product 5 was bigger than 2, and it's endothermic. Okay, so whenever the products are greater than the reactants, it's an endothermic reaction. If the reverse happens, it's going to be a negative number, because this number is going to be smaller than that one. So it's going to be negative when you subtract. Okay, so that'll be exothermic. Now we can do a coffee cup calorimetry to measure enthalpy in an experiment. If you're in class, we could do an experiment. They call it a coffee cup because you're looking for like kind of an insulator cup with the top on it. So coffee cup, you can do it with like a styrofoam cup to find out. So what you do is you kind of figure out the energy before and after the reaction. You measure temperature and different things going on with that. Because it's very, it's not so easy to determine the amount of energy in a molecule. And it's because it's difficult to how much energy is in that bond. It's like we can't even see them. So it's like hard to see it, or hard to see the energy. So we kind of figure out what happens in the solutions when we make something. When we perform something in water and measure the change of temperature of the water, we can then figure out, using that specific heat capacity, to calculate what's going on. So this is going to bring us back to something I showed you in one of the first videos, is this equation right here. Okay. Sometimes, we have reactions that if we actually put them in our hands, like over here, it burn us because it's releasing heat. It's exothermic. Okay, so we use this equation to figure out what heat is released when we do this like solid kind of reaction. So what we're going to do is the same old thing, is the same as before. A couple weeks ago, we're going to plug these formula or numbers in for it. And yes, they're going to start talking about moles for a little bit, which I know some of you, it's like flashbacks when we talked about moles not too long ago in class. But anywho, so we have that the temperature of the 550 grams of water increases from 22 to 27.53, and the specific heat capacity of water is 4.186. Okay, we know the temperature increased by 5. Remember, we're going to take the difference. You subtracted these two numbers, okay? Because for the change of T, you need a subtraction. You can use the equation above to find the amount of heat. Okay, so we're going to plug all those numbers in. So 50 was mass, grams, 50 grams. The C is at 4.186, the one they gave us. The capacity, or specific heat capacity, is right there. And then 5.53. Remember I said they took the difference between these two numbers and subtracted and got 5.53. Oh goodness, now we got to plug it in. So let's pull up our calculator. Okay, so I have 50 grams. Okay, times 4.186 times 5.53. Okay. Well, now they want it round it to the nearest 10 kilojoules. Huh? So you need to make sure it goes to the 10th right there. So let's round it up. 1,160 should be. I tried putting it the first way a few times. It took me a little bit, but yes, round it to the nearest 10 kilojoule. Okay. So let's move on. So now let's try another one on below. Okay, let's see. So when it's dissolved in water, it heats up the water, calcium chloride. Okay, a coffee cup calorimeter is used with 50,000 grams of water. 2 moles of calcium chloride is dissolved in the water, and the water's temperature increases from 20 to 20.8. Okay, which equation shows how to calculate the amount of energy? So we're going to use the Q equals MC change of T, but we got to make sure it's plugged in correctly. Okay, all of them say 50,000 grams. Yep, because we know that's M. They're all right. Okay. Now, the next one we need to use is C. C. Well, what's C? C is always the specific heat of water, which is 4.186. Okay, oh, we gotta eliminate this one. This one doesn't have 4.186 as the C, so it can't be that one. Okay, the last one is the change of T. So take the change of temperature. 20.8 minus 20. And if you need to see it, all you just do 20.8 minus 20. 0.8. So which one only has the 4.186 and 0.8? There we go. Check it. Correct. Okay. Now it wants us to solve for it. Okay. So let's plug it all into our calculator this time. Now it wants us to convert though from joules to kilojoules. I'll mention it at the end once I plug it in. So 50,000 times 4.186, okay, times 0.8. Oh goodness, that's not an answer. But remember, we're going from joules to kilojoules, so we move the decimal place 3 times to the right, so or to the left. Sorry, 1, 2, 3. So 167.4. Check it. Okay. Now, this is where we bring in the moles a little bit. When 2 moles of calcium chloride was dissolved, 167.4, which was the answer we got last, was released. Okay. Calcium chloride is kind of like a salt solid. Anyway, it's dissolved in water. Okay, what is the enthalpy of the reaction? Oh, so what do you think I do? So what's important right here is to know it's 2 moles. Okay, and 167.4 was for that 2 moles. Well, how are we going to figure out for 1 mole what's going to happen? Because we're looking for kilojoules for 1 mole. So I really think all we're doing is dividing by 2. Okay. Now the thought is it negative, is it positive? Remember, it's releasing energy, so it's going to be a negative exothermic reaction. But anyway, we're going to do 167.4 divided by 2. 83.7. It's going to be a negative number because it's releasing. It's exothermic. Okay? There you go. There's your review. Okay. Now, this one's a little bit different. I'm going to start this and kind of finish this in my next video because this next part's a little bit difficult and to understand, but I want to start it now and then review it more in the next video. But the next time is does not depend on the steps in intermediate steps. What does that mean is it doesn't matter from like point A to point B, but that you kind of move on. Okay? It doesn't matter the steps in between. Okay? So, think about it this way, okay? We can go from Johannesburg to Durban, South Africa, but we could stop at other places. We can go along this way. It doesn't matter, okay? So, the steps in between doesn't matter. And the same thing happens with reactions. Okay. So, we have this whole law called Hess's law. It was this person that states that a reaction does not depend on the path, okay? To use this, we've got to use reactions we already know this enthalpy change, this value for it. And then we kind of set it up algebraically to figure out the reaction we're interested in. Now I'm going to show you what's on Apex. I'm going to show you a kind of PowerPoint or the notes you would be taking in class a little bit more about it for it. Now, you're taking 2 or more reaction equations to get the equation you want. Okay, to use Hess's law. Okay, so to find the total enthalpy of this reaction for 2NO2 makes N2 plus O2, you can add the equations of 2 related ones, which you already know the enthalpy of. okay? And you add up the final. So it's really just kind of adding things, which is not hard, it just looks complicated, okay? So we know this reaction here, we know this reaction there, we're going to put them all together. So like this N2O4, it goes on the left side of the arrow. So does this 2NO2, because they're both on the left side, so we place them on the left side of the arrow, okay? Everything that's on the right side of the arrow over here, we're going to list all three things. 1, 2, 3. Those are three different things. We're going to list them over there. And that's really all you do. You just algebraically put these two things on the left side of the arrow, these three things on the right side of the arrow. Okay? So in the end, though, if you have something that's the same over here, so that's the same as is that one, okay, we got to cancel them out. If it appears on both sides of the arrow, it cancels out. And so in the end, we get this, which is the reaction you want. Okay? So bear with me. So now, when you add these up, we know the enthalpy of this first reaction. We know the change of enthalpy of that one. We can, in the end, just add these two together to get the total. After we put all of the chemical formulas together, we can then add up these, and that's our total reaction enthalpy that's released when this whole reaction happens. It's exothermic because it's negative, and then that's what's going on. So that's Hess's law in a shortened form, okay? I'm going to kind of go quickly a little bit through this as well, okay? And so Hess's law pretty much just said if you add two or more chemical equations to get an overall equation, you can also add the heat changes, okay? So we're trying to see, we don't know exactly what one reaction is, so we can use other parts of reactions to kind of figure it out, the change overall. Okay, so what we do is we identify, if the two identical substances are on the opposite sides, they'll cancel. Like I said, if you find one on the left side and one on the right side and they're the same thing, they're going to cancel out. Okay, and then if they're two identical substances on the same side, you add the coefficients together. And I'm going to show you an example of that. And then the other kind of is keep substances on the same side of the arrow in the final equation. You can't move from left side to right side. They're going to stay on the same side. Okay, for example. Okay, so when I add the following equations, I've got C, carbon, plus O2 makes CO2. Then you've got CO2 making carbon monoxide and 1/2 of oxygen. For right now, I know we never had halves as coefficients, but for now and for this Hess's law, we can do that for now. And it's helpful to start by aligning the arrows next to it so that you can see what's on the left side and you can see what's on the right side. That's like a helpful hint, okay? Because all you're doing is literally adding what's on the left and right side, okay? First things, though, we canceled out. If the same thing is on the left and right, we're going to cancel it out. It doesn't need to be over there, okay? And so, well, 1/2 of an oxygen, so we're going to cancel out because there was a full one. So if I go back, okay, so 1/2 an oxygen here, but a full, think of the one being there, well, I can cancel 1/2. That's what they're kind of doing, okay, with this? Okay, so what we're left with is a C plus 1/2 of O2 equals CO, okay, because 1/2 of O2 is O, okay? So, but C, 1/2 of O2 equals CO, okay? So I kind of want to give you the idea that we can do this, and I'll show you more about doing different things with that as well. Oh, let me finish that. I think that's a little valid. So if we do this one as well, this one there's nothing to cancel out generally, but this is just showing you that we can add coefficients. If there's 2 coppers, there's 4 coppers here, you can add the coefficients and figure out kind of what's going on with that. This is different than that one over here, so yes, you're going to put both of them on the left and right side. Okay. I know I'm kind of running up to the 15 minutes that the screencast kind of has, but I want you to try a little bit of this. If you get further than this, it's talking about trying to put them all together using the equations, and I'll show you more next time in the part 2 of this when we start to have put moles back in there.